welcome back to the Torras AI podcast. Today, we have a very special guest, Gerald Friedland, a leading expert in artificial intelligence and machine learning. Gerald is a principal scientist at Amazon Web Services, working on AutoML. He's also an adjunct assistant professor at UC Berkeley, where he helps create new data science courses and teaches graduate students. Gerald is also part of the faculty for the ADEN Business School. He's co-founder of Brainome, a company focused on no-code machine learning, and has worked as a principal data scientist at Lawrence Liverpool National Laboratory. Gerald even started his own company, Odim, making smart devices that understand sound. Gerald is recognized as one of the most influential scholars in AI. Get ready for an exciting conversation about his career and the future of technology. Gerald, welcome. How are you?
Thank you so much for the for the intro, and I'm very blessed to be in your podcast. I'm really well, thank you.
Oh, thank you for being here with us. So tell us, how is your daily job as principal scientist at Amazon Web Services?
Yeah, so it's a great job. Basically, that's the quick version. The more detailed version is it's really challenging if you, as a scientist, feel like you really want to move the needle, sort of work on stuff that's literally at the edge of the edge of the edge of the most forefront. um, that's what basically Amazon can give you. And you're gonna work on stuff that people think isn't yet possible, literally. So that's what excites me about it. And for me, it's interesting. I'm using lots of my experience, so it's not just experiments in my case. It's a lot of also applying theory and cutting down on the experiments you don't have to run because you know they won't give you any results. And that is important because Amazon is moving extremely fast. It's not just the Prime delivery that's fast, everything is fast. And so knowing where to go before you even go there, instead of just guessing and checking, tapping into the dark, is very important. And I enjoy that a lot, to just basically be challenged every day. Yeah, so that's my job.
That's amazing. So, well, what a year for AI, huh? So we've seen a lot of things going on in many areas since ChatGPT got popular in the first place. That has sort of triggered an avalanche of AI and innovation. So, for you, what are the main accomplishments that we have lately got into with AI?
I think the interesting shift that I see now is kind of twofold. One thing is people realize the AI is not exactly only machine learning where you classify and regress, which is a very important part of AI that, by the way, will not go away. It's still the foundation and the very important part of AI is machine learning. However, there's now for the first time that we see that you basically the generative part of AI, especially for language, but also for, as we know, videos and images, has become productive and has become valuable. And so there is now a different value proposition on top of the value proposition that we had before. And of course, that created a huge boost and makes it basically part of mainstream media. And that is for somebody who, like me, started doing AI in the beginning 2000s. I think 2003 is the first time I built a neural network. Is kind of interesting to see because all the fundamentals, if you worked on this for so long, you know kind of where you can go, what can be done and what cannot be done. But of course, with the hype comes now a bunch of promises that some of them you already know like can be done. Some of them, and these are the interesting ones, you go and say, wait, maybe it can be done. And then it sometimes happens so fast because we have this exponential growth of the field. And so that is the challenge. That is really like going in on that wave, being on the edge of the edge of the edge, as I said earlier, requires you to basically run a marathon. You have to really sprint
Oh,
and understand what's going on.
yeah, absolutely. And I think you used the word hype, right? Or I would call it exaggeration or over expectations. And folks who, like you and me, right, have been in AI for some time, we remember the idea of AI winter, right? When it's like, okay, because of all this over promising, not delivering, eventually investors would say, hey, that's not working. It's never going to work. So we saw an AI winter happened.
So yes, and so I want to warn people about this, and this is important. So we had a first AI hype when the perceptron came out, and the first neurons came out. They were, by the way, these perceptrons and neurons were electrical components. Okay, these were not like just the equations in a computing system. These were electrical components. And then one book came out by Marvin Minsky, who was the head of the MIT AI lab at the time, and he just said, well, it's not worth looking at the perceptron because it can't do XOR. Well, if you think about it right now, especially in hindsight, why would that even be a problem? First of all, you can stack neurons together, and of course, then they can do XOR. Second, there's features you could extract, or there's even in my book that I recommend, and we talk about later probably, is that I show that you can have a bijective function, just basically expand the dimensionality of XOR, the input of XOR, and of course then one neuron can do it. And so now the question is here, so there was never a technical problem. This was also not a hype overpromise. There was just a political movement to basically get this, to curb the progress. And we've seen that a couple of times. And this is why we have to be very important. So first of all, you also have to understand, why do these political movements come? There's all kinds of reasons, right? But I think the major reason that I want to say is, whenever you have a hype, of course, you have people you also fear, right? So there's a hype, fear, contrast. And then sometimes the fear takes over, and then sometimes, well, first of all, right now we have a hype, but it's completely clear, we already know, we talk about the ethics of AI, and we talk about people who are really afraid to lose their job. And so to get to this, first of all, don't believe all the hype, right? So number one is, yes, when somebody is excited, there's every action and reaction, right? The reaction to somebody being super excited is somebody's fearful, right? So if a powerful person like at Google or Microsoft and so on, and go and say, we're gonna make all the jobs away in the next 20 years, of course that's fearful. I'm sorry.
People get scared, indeed.
Yeah, it's very scary, and it takes a lot of education to know not to believe this right away. Okay, and I'm gonna explain to you my view on this, obviously. But the interesting part here is that the easiest way to look at this is, as if you talk to any historian, right? The best prediction for the future is the past, okay? And the best prediction for the future is the past means, in this case, well, what has AI done in the past, right? So in the past, AI, and we need to really go into the past. What's the first AI ever? Well, the first AI ever is we could do arithmetic automatically. Yeah, there was a job called computer, was a person job.
That's right.
The job, because there was a senior computer and probably an assistant and an associate computer and all of these, right? So like a real job.
Yep.
And of course, that job went away. But how quickly did it go away? Did it go from one day to the other? No. The computer was invented in the 40s. And how long did it take for everybody to have access to, let's say, a pocket calculator? And or for the people who hired computers, that was probably somewhere in the 60s. I had to double check actually.
That's right.
But it's not just a year or two. It took a long time, almost a generation. And so the next thing is, okay, that was the first one. What's the next one? Well, I think in some ways, secretaries, right? So when you think about in the past, of course there's many, but I'm thinking about the big ones. Secretaries, because we have Word, right? So now instead of when you type something wrong, you have to use Tipex and find out ways to correct it. So you better make not a lot of mistakes when you write a letter. That was the job of secretary. Now we had Word we can correct, and then we got Word to and other text processing to actually autocorrect, and even we go so far that now we have things like Grammarly, where you go and it's like basically almost writing it for you, and then now we have ChatGPT, who's completely writing it for you, and you just have to go through it and make it a little sharper. So yes, that is actually the development. Now, will we get rid of novel writers? No. Will they, however, be helped by AI? Absolutely. So in the history of AI, there were, yes, a couple jobs that went away, okay, but also not immediately. But mostly what it did is, if you really think about it, it increased our productivity overall, right? And so I would say we hire more people now that teach people how to use Word and that actually work on Word. And then we had secretaries, or we could have secretaries. That's the other problem, right? So that means it increased our communication, which is usually seen as a good thing. It increased our ability to write things quickly and sharply in the end. So I don't need a secretary for that. I can just do it. And it means, for example, that a worker who's at, let's say, I don't know, storage worker, let's call it storage worker, they can write a letter and say, hey, things aren't right. And they can just use Word and Grammarly to correct it and send it to the high
That's
ups.
right.
That was not true before. So actually, we enabled a bunch of things that we forget. When we just think about, oh, yeah, it was so nice to have a secretary. Well, okay, I get it. But overall, the productivity went up. And now you could ask yourself, okay, did we need this productivity going up? Well, that's a good question. But we have to think about the fact also that our population density goes up, right? So as we have exponential productivity increase, we also need to, because we have exponential population increase, right? Of course, and we're not going into this, a problem with the distribution of how this productivity went
Where
up.
this population is, right?
It's a different story, right? But in the end, if we didn't catch up with productivity, then the problem is, would we even be able to handle this, right? So in the end, the computer itself was AI, right? And it just pushed the envelope further and further and further. And what we changed was the entry barrier. In the beginning, in order to replace or assist a computer who did arithmetic, you had to wire the computer, like in the very 40s. Then there was assembly code. Then there was programming language. And, I remember programming C and having to allocate memory myself and so on. And it's still actually
Same
cool.
here.
By the way, C is still super effective. I love C. Anyway,
I
and
love
now
it too.
when it became Python, we could make it more mainstream because Python was easier to understand for people. And now it looks like we can do not all, but a lot of simple programs using generative AI. And that's cool too. It just means we're going to be even more productive in all of these
Yeah,
areas, right?
yeah, absolutely. That makes sense. And if you look at Amazon Web Services, I believe it kind of triggered an era of innovation and what we call software as a service startups. I believe that at some point, 99% of these companies were using Amazon Web Services as their computing power. So that's and that brings me another topic, right? You mentioned secretaries. It's like kind of understood as the people who would write letters or
Right.
use type letters when they were basically being dictated a number of sentences, right? But now we have, of course, software engineers as well. It's not secretaries that we are talking about. Software engineers. I don't know. A couple of years ago, there was a big demand and big salaries in some areas like Silicon Valley, where you are, and I was a couple of years ago. There was a really big demand, and now something is happening. I see there is a shift now, and what we see is generative AI can generate very efficient code as well. So, what is your take on how AI will um, what's going to be the role of AI when it comes to produce software, which is nowadays
Yeah.
I believe the main path to
So
innovation.
I want, and this is very simple to back up what I'm going to say. So I want everybody to just try, go to any of the, ChatGPT, Claude, Gemini, and so on, and ask it to write some software. And you're going to see the maximum kind of software you can get out of that is about a page long, right? Now you tell me
Correct.
how many lines of code does an average software, even an app, that simple app, have? A lot more than one page, right? And
Tens of
so
thousands,
you go,
at
right?
least.
Exactly. Usually tens of thousands of lines of code. And so what that means is, yes, you can write small snippets automatically now, and then you have to put these together. So what does this mean? Well, this means, like, yeah, you're not going to get hired to write like one small method anymore that was basically, by the way, previously copy pasted from the web anyway, right?
That's correct. That's right. Yeah, we all know
So,
Stack
no,
Overflow and this kind
I
of
know.
websites.
So
It's
exactly.
it was already
So,
there.
and
Yes,
that's the point. So most of the software that ChatGPT or Claude or Gemini, all of these can write, is basically things that came from ChatGPT, and then it generalizes a little bit. Sorry, things that came from Stack Overflow. Sorry, things that came from Stack Overflow, and then it generalizes a little bit. And that's exactly it. So does that make a full-fledged software engineer? Absolutely not. What it makes the life easier of a fully fledged software engineer. It increases their productivity. But if you ask any software engineer with a little bit of experience, they'll say, no, 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 the big thing is to think about the architecture. How do I make the simplest solution possible? How do I sort of make everything self-integrated, use the least amount of libraries, not have all these dependencies that are going to maintain down the line? There's all of these engineering skills, right? So we get to the point where we say, okay, if you actually want to build a house, right? You don't. Is it a problem that you now can buy components like 4x4s and and screws and so on? No, it's not. That actually just makes your life easier, that you don't have to start and do everything from scratch. And of course, originally, and it's a long time ago, I know, you had to do all of this by hand, right? If you try to build a house by yourself completely, you have to do the 4x4s yourself first before you build the house. And so it's normal progress that you can outsource um, so basic components to somewhere else. Now we outsource them to a chatbot, and that's super convenient. That's awesome, but it doesn't take a software engineer away, because a software engineer is gonna have to handle sort of the entire and the growth of the system. So if you, for example, ask any open source maintainer, that's also very approachable and easy to do, is like, or you look into the news, like Linus Torvalds, what is his most important job? Is not to write little snippets of code, is to look at all the little snippets of code that come from various people and say, this one is important, we need to get this in, and this one is kind of not important and it breaks 50 other things.
that's
Right?
right. Yeah, yeah,
So
absolutely. So it
that's
makes. I think that that's probably in general about AI. It takes away all these sometimes big, sometimes small tasks that are kind of boring, right? So it takes the bore away from humankind. That's the way I see AI, and I believe it's very
And
positive.
I believe you're completely correct on that. And I would actually back you up on this, because in the end, we have to ask, what is the equivalent of a computer? And we have to be careful, because there are lots of notion like Turing machines, infinite memory, and super difficult finite state machine that we kept in the open, and how difficult it could be, and so on. No, no, no. There are other notions, right? And so one of the notion is that a while loop can actually do everything. And if you don't believe me, first of all, look it up. Second, if you ever looked at what an Arduino does, an Arduino has a main loop. It's going infinitely times, and then all you have to do is put in your code here. Turns out, all a computer actually does is repetitions, right? It can do really, really well. And in fact, the original idea is that, right? So it's too complex to build, so let's say, an adder. We go back to the original computer, right? It's too complex to do arithmetic on decimal system. Why? Because you have a number like 99. Yeah, it's 2 digits, but now you have to think about, could it be 9, 8, 7? There's too many states per digit. If you do binary system, it becomes 7 digits. I hope I'm right here, or 6 digits. I need to double check.
I don't know now.
Yeah, right. 6 or 7 digits. It blows up the number. But now each state is just 0 or 1. And so what this means is, yeah, I can build one circuit that handles 0 or 1, let's say, addition. And then all I have to do is repeat. That's the whole trick of the computer. So if you can map something on repetition, a computer will do it really, really, really easily. And that's what we have to remember. The two things a computer does really well is memory and repetition.
That's
Everything
right.
else, we have to
Yeah.
kind of.
And to some extent, if you look at the idea of large language model, right? Once you have the idea of a neuron and a neural network, and then a back propagation algorithm, then you can add thousands of neurons, and then millions, and then billions of neurons, and then bang, you get the systems that act intelligent, which is what we want, right?
Right. So first of all, there's a bunch of things to say. So number one, and I get this a lot, and people hate me when I say I don't know why, but we need to define intelligence, right? So intelligence originally in 1905 was defined by Binet and Simon, and they used it in a terrible way from psychological experiments that I'm not standing behind, but the definition is still right. The definition was the ability to adapt. Now, the problem with the definition is it works in psychology if you only look at the brain, but it doesn't work if you think about the universe, right? So is sand adapting around your foot intelligent? No. This is action equals reaction, right? So intelligence is the ability to change, to adapt to change, was another popular definition, I think came in 2010s or so. And they just attributed it right after Stephen Hawking's death to him. But turns out if you Google that, there's no evidence he ever said this. And also that doesn't help that much because the change could be the force of your feet in the sand, right? It doesn't help that much.
That's right.
But what helps is you now have to think about what is actually changing, right? The environment could be changing, the tasks could be changing, and then it starts to work. So why is a smartphone more intelligent than a regular phone? Because it has the ability to adapt to changing tasks. And you can change the task by downloading an app, or obviously, actually, if you really think about it, by building an app, right? So now you have to be a programmer. So we are the task changers. And the other thing, of course, that biology does is the ability to adapt to changing environments, right? So our environment changes, we have to adapt. That's our genetic adaptation. And in fact, what is actually the most interesting point of neural networks, that most people don't realize, and it's at the same time the most frightening for me point. So am I afraid of some parts of AI? Yes. So the most frightening point for me is that we found an algorithm, in this case, stochastic gradient descent, or in general, just backpropagation, but stochastic gradient descent works to learn everything. You can adapt any memory structure, like a decision tree, a neural network, whatever you want to adapt. It could be a spin on neurons, a spin of magnets too.
So generic algorithm, you can train it to learn anything. Yeah.
And you can use that to learn anything. And while this is an unbelievably enormous feat of science to come up with a learn anything algorithm, we have a problem, because that means, because it's so general, it's overly general, that means we can't explain anymore. Why did it learn what it learned? Because it learns anything anyway. And so that is the problem, that the machine learning field is built on ignorance. We are proud of that ignorance. We are proud of the fact that we don't have to know how we learned what we learned, because we can learn anything with this algorithm.
That's correct. And that is frightening. It is anything but explainable. AI is not explaining why it's taking decisions. Absolutely.
And now they go and say, yeah, the answer to that problem is that they say, no, let the model learn how to explain. Oh, that's not biased at all, right? So where I want to go is this. We have very complicated system. And all the other problems that people say, it has so many parameters, good luck changing it. No, here's a very complicated system, your CPU. Okay, the CPU in any computer is a very complicated system. It has millions of transistors, also again switches, like neurons, right? So millions of switches. But when we had a problem with the Pentium that came newly out in the 90s, you know what happened? Intel said, oops, I'm sorry, we're gonna fix it. And they fixed it. So what they did is they sent a software patch for everybody who had one of the faulty ones. And then they asked the engineer who was in charge of that particular part to fix it. They fixed it, that was it.
That's right.
What if we had a problem in one of the backpropagation, is SGD trained neural networks? How do you fix that?
That's right. It's like, no problem.
Now,
We'll start it over
yeah,
from the beginning again.
yeah, exactly. Why would starting over fix the problems? My next question, right? So the trick with science is that we use incremental updatability. We are able to fix errors. We are able to question things. And the science is all about consistency of explanation. It's all about incremental updates. So people don't realize Einstein updated Newton after hundreds of years. That was the big interesting part of relativity. And you can do that. And that's the interesting trick of science. There is this updatability. If we get rid of the updatability, we have sort of a problem. And that is the part where I start to fear things, because I'm like, okay, are we going to just make these neural networks so powerful that we are completely not anymore updating anything and they take their life on their own and then we completely lost control? So for me, if you want to discuss ethics and accountability, it's make things updatable again, make things correctable again, and make things so that we keep the control over all the details.
Yep, which is certainly not happening now.
Exactly.
Hey, you mentioned Albert Einstein. That's great, and we had our conversations prior to that, right? So there is one thing that I would like to uh, announce, right? It's you, right? Is now and here, Gerald Friedland coining a new term, and I find this very exciting. Is the idea of computics, right? We discussed that computics, which is kind of computer and physics, I believe. That's why Albert Einstein came to my mind. Could you tell us what is computics, Gerald?
Yes. So as I said, I have a long history of teaching at many different institutions. Like again, I taught in Berlin. I taught in Aden Business School, which is South America, and definitely also at Berkeley. So I actually taught of three different continents in different systems too. I taught in adult school. I taught in sort of applied university, actual university, and sort of Berkeley. There's an elite university. All of these kind of I know all of these kind of scenarios. And what I find is I continuously found that we're getting rid of the fundamentals in favor of just teaching for the first job, right? And the
Right,
mistake here is, of course, so first of all, students want that, and I understand why. I understand that it's very difficult when you're young to understand that actually it's all about fundamentals. Once you get those right, you can adapt to anything. Because really what we should teach people is to adapt to anything. Because remember, that's intelligence. We should make them smart, means
right.
to adapt to anything. So how do we adapt?
Adaptability is intelligence.
Ability is intelligence. So we should be able to have a student adapt to any job in their field. That's the idea of a university education versus a trade school. Right? A trade school is, hey, let's give some practical skills. Let's get you started right away. That's what people want. I need money now, and I'm just going to work my way up in the system. And that's totally fine too. But also, we should have people that learn it sort of to adapt on a sort of different level. Like we want a diversity of people. And so now here's the point that even if you look at the new data science curriculum, and I actually brought this up, I said, how is it that in the new computer science curriculum, we never mention the bit? There's no mention of the bit. If you look into theoretical computer science literature, I want people to maybe put in the comments and point me to links where in the theoretical computer science literature is the bit mentioned. It turns out it's not. It's very hard to find. Richard Feynman uses it. Interesting. So the more we think about it, but the most important inventions, Claude Shannon, who actually wrote a master's thesis that most people don't know about how to use relays to implement Boolean algebra, which literally is the computer, right? It's just
The foundation of computing is the
was
bit,
invented
which
in
is
parallel.
the Boolean algebra. Absolutely.
Exactly. So it was
And the
invented.
idea of information theory, right? And how do you measure information?
Exactly. And nobody measures information. So why are we not measuring? Why are we not teaching the bit? What's going on here? And if you look at the data science curricula, they're composed of statistics and programming and some basic math too, like probability and so on, which is important. And I'm not saying none of these fields is important. All of them are important. But the one field they're missing is physics. And now we have to ask ourselves, why are we missing it? And what's different now? The first one is, why are we missing it? Well, we're missing it, I think, for two reasons. One is political. There was a big anti-physics movement in the 60s, obviously, after the nuclear bomb was created. There was a big anti-physics. I understand. It's like a frightening event, and it's just the same winter we had with like other ones we have to fear about. It's what it is. And there was atomic hype. Oh, let's build nuclear plants everywhere. Not a good idea, we know, but the point is, hype is bad. Full stop, right? So let's put it back to equilibrium. And unfortunately, if there's a huge hype, you get a big fear, and so we got rid of that. And also, there's a reason why in the beginning of programming, let's call it Fortran, and all of these initial stages of computing, we didn't need physics. Because if you build, let's say, a Pac-Man game, you can do that completely devoid of physics. You don't need physics. But here's what changed. What changed is that we're now doing machine learning and AI. And what is machine learning and AI doing? It looks at data. What is data? Well, data is observations. Now, math itself and even statistics is just counting, right? Let's be frank. Does not have any way, it's overly general. It generalizes away from observations. It usually starts with anecdote. Let's have 5 red balls and 5 green balls in a drawer. Like, this is how it works. It's anecdotal. The one science that tries to approach things universally, in fact, literally, you want to understand the universe, it's physics.
That's right.
Now, do I believe that we need to teach everybody physics and all physics? No, that's not what I'm asking about. But what I'm asking about,
It got complicated, right? When you get into
complicated,
quantum and relativity, like it's not a high school
I will tell
topic
you
anymore.
a joke. I actually work with a quantum physics group inside Amazon to help me understand a lot about large language models, by the way.
Oh, wow.
So, most
That's
people
amazing.
would be very surprised how much you can understand about large language models once you understand the principal math of quantum physics. So the
That's
interesting
amazing.
part, so okay, just for the geeks out there, think about this. What's a quantum state? Like, let's call it, in the Brakeh notion, X, like Brakeh X,
Not an expert in quantum
just
stuff, but I
X
know this notation. Yes.
exactly, X pi y.
Yep.
Put that into a finite space and you have a perceptron. That's the interesting part. The quantum state is a perceptron. Why? Because it's just an inner product. An inner product is just an infinite dot product. Guess what? If you threshold that quantum state, that's a perceptron.
Wow. Wow.
So
That's
the
amazing.
interesting part here is there are these commonalities. And why are they there? Totally coincidentally? No. Because who's the first one who modeled observations? Isaac Newton. He asked, okay, I have this observation, the apple falls down from a tree. How do I model this with math? So he looked at data. The first data scientist is Isaac Newton. And so now the problem is not that we need to just learn physics. No, there's a lot more to it. But the problem is ignoring physics will not help us at all because the fundamentals are there if you ignore them or not. In fact, knowing their fundamentals will help us understanding things. So how is a bit of complexity connected to energy, for example? These are posts on my LinkedIn, but also in my book. The interesting part is that notions like entropy, for example, and information theory are directly connected to energy. That's what Richard Feynman. So for example, Richard Feynman wrote a whole book called Lectures on Computation. It explains computer science the physics way. And when you read it, it's so easy to read. And you ask yourself, why didn't I learn it this way? So now you could say, okay, we're just going to redo all computer science. Why would I do this? And I'm saying, well, first of all, a reform is not bad in a field that has exponential growth. And we basically reformed in the 1970s the last time, so I think it's due. But even then, I would say, fine, right? No, but there's a real demand here. The demand is you are a business major and you want to actually not learn to program. Also, why would you? ChatGPT is doing the microprogramming that you would learn as you would not do
Yep.
more microprogramming in let's say a semester or two anyway. You don't want to become a software engineer that does the big tasks. No, you all just want to know enough that you can understand the limits of where this is going and you don't fall for a hype or in an extensive fear. That's what education does, right?
Yep.
Education helps you overcome those fears and hypes.
And hence you say, okay, I have computer science, I have physics, let's put that together. And that's where the word or the term computics come from. I love it. That's amazing. Listen, you're talking about a book here, and I cannot just pass this opportunity to talk about it. Where is it? How is it called? Where can we buy it?
Okay, so it came out in December 2000, last year, 2023.
All right.
Right, and it's basically it's an interesting a point where it's like the pre-Computix book, I think.
Nice.
So you'll see a lot of chapters there that ask the why questions in computer science. Again, if you just Google it, it's called the information view on machine learning, and it's basically it's data science as an engineering.
So the title is Information
Okay, let me
and Learning. We have to put that
okay,
super clear because I'm going to put that in the transcript as well.
So the title is Information-Driven Machine Learning, Data Science.
Information-Driven Machine Learning.
Yeah.
By Gerald Friedland.
Yes.
And I guess it can be bought at Amazon.
Yes, you can buy it at Amazon.
Nice.
Also, you can buy it anywhere. It's like it's a book. Any bookstore has it, and you can also get the online version from Springer. In fact, what I want to say is there's two things coming about this book. One is there's a German translation that will happen soon. Like I think in summer, it's coming out. They're working on it.
Right. So the original is in English and is being translated into German.
Yeah, it's kind of very interesting. I'm German originally, so yes, they asked me, "Oh, can we translate it to German?" And I said, "Yes, but I want to read the final copy." And that's actually not part of the standard contract because most people don't speak German. I was like, "No, but I want to read the final copy," so I had to change the contract for that. But that's fine. This was one interesting part.
The most in defense of German is the most spoken language in continental Europe. My home language is Catalan. You probably didn't even heard about that.
Of course I have, because I also speak Spanish and I've lived in Spain.
Okay.
But Catalan, yeah, I know. Well, it could be more strange.
It's going to take some time before it's translated to Catalan. Let's put it like that.
I want to have a Spanish translation. So if anybody, I talked to my publisher, they won't do it, but they said if you find one that translates it to Spanish, we'll support it. So if you want to.
Awesome. So for the audience, a call here. If there's somebody interested in translating an amazing book with incredible ideas,
and so
here we go.
Here's your motivation. Once this comes out, we'll have 10,000 downloads in the last 6 months.
Bang! That's a price. 10,000.
10,000 downloads, and that's for a text.
Awesome.
Right.
Awesome.
I mean, with Harry Potter, I know it would be nothing. It's not a New York Times bestseller. It never wanted to be. It's a textbook that crisply explains the limits of AI, why we do things in AI the way we do it, what we should be doing, and why things actually work the way they work.
That's amazing.
Basically, the principles of understanding it in physics, but not explaining it in physics, explaining it in because it's so related and much easier to understand for computer scientists to just explain it using bits and bytes than, let's say, using right?
Awesome. Gerald, thank you so much for all this time. I want to be respectful for your time. And before we wrap up, I would like to ask you, what is the best way to contact you?
Oh, yeah. So LinkedIn.
Awesome.
I love LinkedIn as a platform. I actually encourage everybody to look at there. It's for me, it's a new version of social networks where you actually socialize with with your business network or with the people that are in your field, right? And you can discuss things on a higher level than, let's say, on Twitter, right? And
Yeah,
so X now. And so that's what I love about it. And I'm not chasing, hundreds of millions of followers. I'm just want that, people in my field know what I'm doing and what I think about, and then I want to hear from them as well. So that's why
absolutely.
I encourage LinkedIn.
Absolutely. Thank you so much, Gerald. And for the audience, they know I'm going to put the link to Gerald Friedland LinkedIn page. Thank you so much, Gerald, for sharing this time with us. That's been an incredible experience.
Thank you so much for having me, and thanks for very, very excellent questions. I love.
Awesome. And for the rest of the audience, we will see you very soon on the next chapter of Torras AI. Stay tuned. Have a good one. Bye bye.